Swayam Prabha. Digital India. Educated India.
So, warm welcome to the 12th lecture on the subject of digital signal processing and its applications. We continue in this lecture with our discussion of the discrete time Fourier transform, its properties, and we also establish examples of some discrete time Fourier transforms. We also establish when we do not have a discrete time Fourier transform, and that will lead us to another transform that is more generalized. So, let us recall the property that we had briefly discussed in the previous lecture, namely where we looked at the multiplication of two sequences and find out what happened in the Fourier domain. We also saw something very interesting when we evaluated that expression at 0 frequency, and we were discussing that and coming to some conclusions from that point. So, let us recall what we were doing the previous time. We saw that if you have two sequences x1 and 2, both of which have discrete time Fourier transforms, capital X1 and 2, then x1n, x2n has the discrete time Fourier transform 1 by 2 pi integral from minus pi to pi x1 lambda x2 omega minus lambda d lambda, which is essentially like a convolution of capital X1 and capital X2, save for the fact that this convolution is evaluated only on one period. I must here emphasize that this is commutative. So, of course, x1n, x2n is the same as x2n, x1n, that is obvious. It is clear that this can also x1n, x2n also has the DTFT minus pi to pi 1 by 2 pi x2 lambda. So, it does not matter which one you fix and which one you move. This is not a very important observation when you have very similar DTFTs, but there are situations where it might be preferable to fix one of the DTFTs and move the other, and therefore, you have full freedom which one to fix and which to move. That is what is being emphasized here. Anyway, we had taken the specific case of omega equal to 0. And we came to a very interesting conclusion. We said summation n over all the integers x1n, x2 conjugate of n is the integral of x1 lambda, x2 lambda conjugate d lambda. We had come to this conclusion. Now, we were trying to interpret this conclusion, and of course, we had an easy interpretation for the left hand side. The left hand side is the dot product or the inner product of the sequences x1n and x2n. The point was to interpret the right hand side, and of course, not just to interpret the right hand side, but also to give it a corresponding meaning, to bring parity and congruity in the meanings on both sides. You see, on the right hand side, you have a product of corresponding points on the discrete time Fourier transform. Of course, the second one is complex conjugated, like it is for the sequence here. You multiply the sequence by each point of the sequence by the complex conjugate of the corresponding point on the other sequence, and you add up over all such points. Here you multiply corresponding points on the discrete time Fourier transform, that is you multiply the point on one discrete time Fourier transform by the complex conjugate of the other, and you integrate, because here the variable omega is continuous, it is not discrete. So, we need to think of this also as an inner product, because we are, you see, if you look at it, what is the discrete time Fourier transform really? Let's look back at the inverse discrete time Fourier transform to fix our ideas. So, the inverse discrete time Fourier transform says that you can reconstruct x n from the discrete time Fourier transform in the following way, and we have already given this an interpretation. These are like the coordinates with different directions, different omegas are different directions, so to speak, or different omegas give you different axes, and you see these are different basis vectors. I mean, there are different basis vectors for different values of omega. Now, let us get this idea clear. What we are saying is that for different values of omega over any contiguous interval of 2 pi, each omega gives you a different so called, I mean, you can call it a perpendicular direction. I mean, I do not know whether it is a correct thing to do, but you can call it a perpendicular direction. It is a different axis. So, you have as many, like for example, in the time domain, every point, every value of n gives you 1 degree of freedom. In fact, if you look back at the way you constructed a sequence from its samples, there was the idea of a basis there. You said that xn is summation k going from minus to plus infinity, xk delta n minus k, and here xk were like the coordinates, if you recall, and these were like the orthogonal basis vectors. Now, here of course this is exact. Different delta n minus k's for different values of k are truly perpendicular. In fact, if you were to take a dot product of delta n minus k1 and delta n minus k2, I mean you have two sequences, it would be 0 for k1 not equal to k2. So, if the impulses are located, if the impulse sequences have the non-zero 1 located at non-zero sample located at different points, their dot product is automatically 0. That is obvious because the sample, the non-zero samples do not overlap. So, these are all perpendicular directions, so to speak. So, any sequence can be constructed from all these infinite, countably infinite perpendicular directions. Now, if we go to finite dimensions, we can recreate this situation to some extent, but as I warned you in the previous lecture, one must not take literally the conclusions of finite dimension to infinite dimension. However, we can get a good clue about what to expect in infinite dimensions when we look at finite dimensions. So, let us look at the very simple finite dimensional case of 2 dimensions. You see, let us consider this 2-dimensional space in which this paper lies, in which the sheet lies. I mean, you can visualize the sheet extending to infinity, constituting a 2-dimensional space. And let us put the origin here. Let us draw 2 pairs of perpendicular vectors. So, one pair is like this, u1 cap and u2 cap. I draw another pair of perpendicular vectors. U3 cap and U4 cap. It is very clear, of course, that U1 cap, U2 cap as also U3 cap, U4 cap form an orthonormal basis. What is an orthonormal basis? An orthonormal basis is a collection of vectors from that space which are mutually perpendicular. Take any two of them, they are perpendicular, and together these vectors span that space. The word basis means they span that space. Span means you can construct any vector in that space as a linear combination of these. So, of course, it is very obvious that you can construct any vector in two-dimensional space as either a linear combination of U1 cap and U2 cap, or a linear combination of U3 cap and U4 cap. That is very obvious. In fact, let us, to emphasize that point, draw a vector and illustrate what I am saying. In fact, we will not draw one, but two such vectors. So, let us redraw these. You have a U1 cap there, you have a U2 cap here, you have a U3 cap here, and you have a U4 cap there, and you have this vector. I will draw a long one, V1, and you have this vector, V2. And of course, it is always possible to write V1 cap as dot product of V1 cap with U1 times U1 plus dot product of V1 cap of V1, sorry, not V1 cap, with U2 times U2. You see, this is the beauty of an orthonormal basis. In an orthonormal basis, you can find the component of a vector along one of the orthonormal basis elements by taking the dot product of V1 with that basis element, and this can be done for each of the basis elements. So, when you have an orthonormal basis, this is the bone. The coordinates are easy to find. When the basis is not orthonormal, you can of course have a basis that is not orthonormal. What I mean is, you can have a collection of vectors. For example, in this collection U1, U2, U3, U4, you can take the pair U1, U3. U1, U3 also form a basis, because you can express V1 in terms of just U1 and U3, or you can express V1 in terms of U2 and U4, and you can do it by using the parallelogram law. You can construct a parallelogram with sides parallel to U1 and U3, and they will give you a linear combination of U1 and U3, which gives you V1. So, using the parallelogram law, you can always express V1 in terms of U1 and U3 or U2 and U4. So, U1 and U3 together form a basis, but not an orthonormal basis. Similarly, do U2 and U4 together. So, the beauty of an orthonormal basis is that finding the coordinates is very easy. You see, if you take U1 and U3, it's a basis but not an orthonormal basis. You can of course find the coordinates by using the parallelogram law, but finding the coordinates is not a decoupled process. That means I cannot find the coordinates of along U1 and along U3 independently. I need to solve two equations for two coordinates. As opposed to that, when I have an orthonormal basis, the job is very easy. I simply take the dot product of the vector along each of these orthonormal basis elements, and there I am, the coordinate comes. Is that clear to everybody? Any doubts on this? So, now we have done this for V1. We of course can do the same thing for V1 with the basis U3 and U4. So, you can write V1 is also dot product of V1 with U3 times U3 cap plus dot product of V1 with U4 times U4 cap. And of course, if you like, I can complete this by putting 1 comma 2 here. So, I can do this both for V1 and V2. Please read this as V1. So, there I have 4 coordinates for V1, the coordinate with respect to U1, U2, U3 and U4, and similarly 4 coordinates for V2. Now, let us write these 4 equations down. What we are saying is V1 is of the form V11 U1 cap plus V12 U2 cap, which is also V13 U3 cap plus V14 U4 cap, where the dot product of V1 with UK is V1K, and similarly for V2. So, V2 is V21 U1 cap plus V22 U2 cap, which is also V23 U3 cap plus V24 U4 cap. Similarly for V2K. Now, the dot product is very easy to calculate because this is a perpendicular basis. So, the dot product of V1 with V2 in this simple 2-dimensional space is V11 V21 plus V12 V22, and it is also V13 V23 plus V14 V24. So, that is what I am saying. The dot product has nothing to do with which basis you use, it is independent of the basis. The dot product or the inner product is independent of basis, and that is not very difficult to see. You can use, if you use orthonormal basis, then calculation of the dot product is easy. You just take products of corresponding coordinates and add. But the inner product or the dot product itself does not depend on which basis you choose, and that is not difficult to see at all. I mean, if you go back to that drawing a couple of slides ago, if you were to take the dot product of V1 and V2, inherently it has nothing to do with what basis you have used to represent V1 and V2. The dot product is a property of the two vectors, not a property of its representation. However, given a representation, one can of course calculate the dot product with convenience and ease. Now, this is exactly what that relationship is saying, and now let me put it back before you with this renewed understanding. So, what we are saying in this relationship, look at this relationship once again. Look at this relationship once again. We are saying the dot product of the sequences x1 and x2 is independent of the representation of those vectors. You could think of the vectors represented in their natural domain, or you could think of the vectors represented in the frequency domain. The dot product is unchanged. And of course, in the frequency domain, the dot product is defined in this way. You need to multiply corresponding points on the frequency axis and integrate over all these points instead of add, because the frequency variable is continuous. So, it is a very elegant and simple interpretation once you think about it. But this very important result has a very central place in discrete time signal processing. This is called the Parsifal's theorem. For sequences, and we are saying in effect that the dot product of the sequences is unchanged whether you look at it in time or in frequency. And there is one specific consequence of this dot product, which we shall see in a minute. That consequence follows if you take x1 equal to x2. We get summation n from minus to plus infinity mod, let us call this x. So, mod xn squared is 1 by 2 pi integral minus pi to pi mod x lambda squared d lambda. And here we have the same specific interpretation as we did for the sequence when we took both the sequences the same in the dot product. The dot product of a sequence with itself, of course, gives you the magnitude or the norm squared of that sequence. We said that when we talk about generalized vectors, sequences are generalized vectors, we do not like to use the word magnitude anymore as we do for finite dimensional vectors. We call it the norm. So, we say the norm, and of course, I also, to be very careful, said that we should call it the L2 norm. That was a technical point. Anyway, for the moment, let us just call it the norm. So, this is the norm squared, mod xn squared integrated over all n is the norm squared of the sequence, and that same norm squared can be calculated in the frequency domain. Of course, the physical interpretation is you have taken the dot product of the sequence with itself, so you are getting the magnitude squared. So, magnitude squared is like the norm squared. And of course, the same norm squared is calculable from the frequency domain. Now, this gives a very beautiful interpretation. You see, what is the physical interpretation of this norm squared? It is easier to see if we look in the frequency domain. What we have said in effect is, if you had a band limited signal, as you started off with when you sampled, then this is actually giving you the integral of the magnitude squared of the Fourier transform of that band limited signal. Now, you see, suppose that band limited signal were a voltage signal, and you applied that voltage across a 1 ohm resistance. The total amount of energy that that signal would dissipate in the 1 ohm resistance is the quantity that you have on the right hand side here. This quantity 1 by 2 pi integral minus pi to pi mod x lambda squared is the energy that would be dissipated. Is the energy dissipated by a 1 ohm resistance if xn is the sampled version let us continue. If xn is the sampled version of the band limited signal, xt sampled at t equal to n for all integer n, xt is the voltage in volts across the 1 ohm resistor and the continuous time Fourier transform of x t is x omega, which is equal to, you see, it is x omega for omega between minus pi and pi and 0 else. So, what we are saying is restrict the discrete time Fourier transform only to the interval minus pi to pi. In fact, here I introduce this idea of the underlying continuous time signal in general. Whenever you have a discrete time Fourier transform, restrict that discrete time Fourier transform to the interval minus pi to pi and cut off all the rest, make it all 0. What do you get? You get the original band limited signal, which was then sampled at the integer points to give you the samples xn. Is that correct? If you take this restricted Fourier transform band limited signal, if you sampled it at the integer points, you are sampling at a sampling rate of 1. What would happen in the Fourier domain? You would take the original spectrum, translate it by every multiple of 2 pi and add these translates. And therefore, you see what let me try and explain graphically. I am saying this is the DTFT. I am showing a couple of periods, whatever it be. This is of course periodic with period 2 pi. Now restrict it. This gives a continuous time band limited signal. Yes, of course. Now, sample this continuous time signal. At t equal to n, that is a sampling rate of 1. So, we get back the original DTFT, because when you sample at a sampling rate of 1, the effect is to shift the original spectrum by every multiple of 2 pi by 1, which is 2 pi on the frequency axis, and these translates are added. So, you get back the original DTFT. So, this is the notion of the underlying continuous time signal. And what I am saying is, think of the underlying continuous time signal for this sequence xn. Let that continuous time signal be the voltage in volts applied across a 1 ohm resistance. The energy dissipated in that 1 ohm resistance is the integral mod x lambda squared d lambda over minus pi to pi. And the same energy is of course obtained by taking the mod square of the samples and adding. So, both of them correspond to an energy. Let us go back to this. So, what we are saying is, both of these quantities are now an energy. This is an energy as seen in frequency, and the same energy is seen in time. So, we also call this the energy of the sequence for the obvious reason that I have just explained. And now we also have an interpretation for just the integrand here. The integral, of course, we have interpreted, it is the total energy, but we also have an interpretation for the integrand mod x lambda squared. The integrand is the way in which the energy is distributed over the frequency axis. So, it is called the energy spectral density, right. Since 1 by 2 pi integral minus pi to pi mod x lambda squared d lambda is the energy, mod x lambda squared is called the energy spectral density. Now, this is not very different from what we understand density to be, say in the case of a mass. How would you calculate the mass of an object if you knew its density at different points? You would integrate the density over the volume on which the mass lies, and that gives you back the mass. And of course, the density does not have to be uniform, right. So, here too the density may not be uniform for all frequencies, and essentially when you integrate the density you get back the mass or the energy as the case might be, right. So, this is what is this clear to everybody. So, we must, this is a very important notion in signal processing, the notion of energy spectral density. Now, of course, though this is not very commonly used, yes, there is a question. Yes.
When we were considering the case of limiting the discrete time spectrum
Yes.
to only continuous time.
Yes.
How can we interpret a discrete time signal into a continuous time?
Okay. So, the question is when you restrict, so let me try and explain the question. The question is when you restrict the spectrum only to minus pi and pi, we are going from discrete time to continuous time. How are we drawing the parallel between discrete time and continuous time? Now, you see, when you restrict the discrete time Fourier transform to between minus pi and pi, it cannot correspond to a sequence anymore. It can't be the discrete time Fourier transform for sequence because it is no longer periodic with period 2 pi. So, it is in fact it is a band limited Fourier transform. So, it corresponds to a band limited signal. Now, which band limited signal? That band limited signal which you had sampled at a sampling rate of 1 to get the sequence that you have. Why are you saying that it is that particular band limited signal? Because if you took that band limited signal and sampled it at a sampling rate of 1, what would happen in the frequency domain? You would take the original spectrum, translate by every multiple of 2 pi divide by 1, because the sampling rate is 1, sampling time is 1. So, 2 pi by 1, and move this original spectrum by every multiple of 2 pi by 1 and add these translates. That is how you get the DTFT, and of course, there is a one-to-one correspondence between the DTFT and the sequence. So, if you are getting back the DTFT by sampling this signal at a sampling rate of 1, then indeed there is a one-to-one correspondence between these samples and that underlying band limited signal. So, for every DTFT there is an underlying band limited signal that you can think of, and that is often useful to do. Is that clear? Yes.
What will be the filter we apply?
So, his question is then what is the filter that you would apply? Well, you see, you would apply the same, I assume you are asking what is the filter that you would apply to reconstruct the original signal from its samples. Is that the question? So, it is the same, I mean when you have a band limited signal, the filter that you would apply is a low pass filter with a cutoff at pi. So, so it would, I mean if you want to reconstruct the signal from its samples, you could think of it as putting an ideal filter, an ideal low pass filter with a cutoff at pi, right? That is what you would do. Any other questions? Yes.
This analogy will hold true only if the signal is band limited.
Well, so the question is, would this analogy hold true only if the signal is band limited? Now you see, we are assuming there is no aliasing, or the other way of thinking about it is, the same samples can correspond to many signals. We know that, that is what aliasing means. Out of them, we are choosing the signal where there is no aliasing. There are of course many signals to which these samples could correspond, but we are choosing that signal for which there is no aliasing, which must of course be the band limited signal, band limited to pi. Any other questions? These are good questions. Yes. Yeah. So yes, there is a question.
These things are only can be written mathematically. Practically, these things are not possible.
So the question is, this can be written only mathematically and there is no practical meaning. That is not correct. You see, we just gave a practical interpretation. We said that, you know, if you took the underlying band limited signal and looked at the energy across a 1 ohm resistance, you get the energy, isn't it? So it's not just a, it has of course a mathematical meaning, but it also has a very important significance. So the word energy actually is very meaningful. It is the energy in many situations. So you know, it's so here in fact that's how the word energy is used. It has, energy has implications in terms of energy as we understand it in physics. So if you have a signal, whether it's a voltage signal, current signal, pressure signal, any other kind of signal which is sensed, this could actually correspond to the physical energy that is being delivered. That is not correct. So it has a practical meaning. You see, one must remember, and this is a comment that I must make in general, it's very important to see the congruence between what we do on paper in terms of algebra and math and what happens in practice, and that congruence is there, right. So one must not assume that one is working out certain things on paper and it has no practical meaning. Everything that we do here has a practical implication. Yes, any other questions? Yes. Okay, so the question is, every or any meaningful real signal is expected to have finite energy. Does it mean that every real signal must be band limited? Now I will give you an analogy again to explain why the statement is not correct, right. You see, we of course know that Indians would always live only for a finite time, right. We can't live for, of course there are legends that people live for 1,000 years and so on, but I don't know of such things happening in the last century or maybe last millennium. So let's assume that people have a lifetime of about 200 years at most, right, 200, 250 years, let's say, okay. So Indians do live for a finite time, isn't it? Now, you know, that is also true of all people in the world. We have not yet come across a person in the world who has lived for infinite time, isn't it? So now, you know, if you say that, now what are we saying, what are we trying to say here? We are saying, see, human beings. So when let's bring an analogy between band limitedness and human beings, right? And again, band limited. So what is the thing we are seeing whether band limitedness and finite energy or reality or practicality is the same, right? Now band limited, it's like asking whether humanness and Indianness is the same. In both cases there is limited amount of life, right? Humanness and Indianness is not the same. Humanness is much bigger than Indianness, right? But both of them have the property that they live only for a finite time. Similarly, finite energy is broader than band limited. You can have a finite energy signal which is not band limited, right? You can have a signal whose spectrum extends all over the frequency axis. You see, take for example the signal which has a spectrum which decays like this. So let this be the frequency domain, and you have the spectrum e raised to the power minus mod omega. This is the spectrum of a signal, a continuous time signal. Let us call this capital X of omega. And of course, the energy in this is easily seen to be finite. mod x omega squared d omega integrated from minus to plus infinity is of course finite. It is integrated of the integral minus infinity to plus infinity e raised to the power minus 2 mod omega d omega, and this is a very easy integral to evaluate, isn't it? It is finite. However, this is not band limited. This is like being human, and band limited is like being Indian in that, right? Both of them of course live for a finite time, but being human does not necessarily mean being Indian. Being finite energy does not necessarily mean being band limited. Of course, being band limited, and if the spectrum does not have what are called, I mean, you are not taking a casual, an extreme example, what is called, I mean, we are not taking a pathological example of a band limited signal where, for example, you have an impulse, a continuous time impulse or something in between, then a band limited signal will of course be finite energy in most cases, except of course if there are impulses sitting inside, continuous time impulses, right. So that's an important question, and one must be clear that band limitedness and finite energy is not the same thing. Finite energy is broader than band limitedness. It's an important question, and I am glad it was asked. Yes, any other questions? All right. So then we've come to this important conclusion that mod x omega squared d omega is the energy spectral density. Now, one comment, just as you can talk about the energy spectral density, technically you should also be able to talk about the energy time density. Though of course we don't use this term too frequently. And the energy time density, or the way the energy is spread over time, is mod xn squared. Notionally that is of course correct, but very rarely do we use this term. The term energy spectral density is used more frequently than energy time density. Yes, there is a question.
When we are calculating energy using this time density,
yes.
So we have sampled the signal for equal to 1 only, like unit sampling.
Yeah, so the question is, when we calculate the energy time density, we are averaging, or we are taking the sampling rate to be 1. Is that the question? Yes, indeed. We have normalized, isn't it? We have normalized the sampling rate. So we have normalized the time axis, and we have also normalized the frequency axis. So of course, when you go back to the actual times and frequencies, you need to bring in that normalization factor. So we are working with normalized time and normalized frequency. Yes. All right. So let's just take one example of a discrete time Fourier transform before we conclude. Take the sequence xn is equal to alpha raised to the power of n for n greater than or equal to 0 and 0 for n less than 0. Now we define the sequence un, which is 1 for n greater than or equal to 0 and 0 for n less than 0. This is a sequence which we call the unit step. The sequence unit step is going to come frequently in our discussions. Interestingly, the unit step itself does not have a discrete time Fourier transform. The discrete time Fourier transform of the unit step would not converge, but multiply the unit step by an exponential, as we are doing here. As we can see, xn can be written as alpha raised to the power of n un. And if mod alpha is less than 1, then we can calculate the discrete time Fourier transform of xn. And that's very easy to do. It turns out to be summation n going from minus infinity to plus infinity xn e raised to the power minus j omega n, which is summation n going from 0 to infinity alpha raised to the power of n e raised to the power minus j omega n, That is a very easy integral to evaluate. It is a geometric progression with common ratio of alpha e raised to the power minus j omega, and the modulus of this common ratio is the modulus of alpha, and since modulus alpha is less than 1, this is a convergent sum, and it converges obviously to 1 by 1 minus alpha e raised to the power minus j omega. So, this is the discrete time Fourier transform of a one-sided exponential. I may also mention that if you have a finite length sequence, if xn is finite length, xn is non-zero only for n between n2 and n1. n1 is strictly, n1 and n2 are finite. They can be positive or negative. It does not matter. Then of course, the dTft of xn always exists. That is easy to see because it is a finite summation. In fact, it is not very difficult also to see that if you took xn here to be the impulse response of a linear shift invariant system, then that system is bound to be stable. That is because the absolute sum of this impulse response is necessarily going to be finite, can't be infinite. There is only a finite number of samples, and of course we assume each sample is finite. So, a finite length sequence always has a discrete time Fourier transform. We have given an example of an infinite length sequence which also has a discrete time Fourier transform. In the next lecture, we shall take an example of an infinite length sequence which does not have a discrete time Fourier transform. In fact, we did it before, but we will take it again, and we will also use that to build a new transform called the Z transform. With that, then we conclude the lecture today.